This conference will now be recorded.
Very good evening, students. Today we are back with the revision sections.
This conference will now be recorded.
Very good evening, students. Today we are back with the revision part of modern physics. And as you know, we are picking up questions from previous year's JEE Advanced Papers on the topic atomic physics, nuclear physics, dual nature of matter, and semiconductor. So we have few questions today from previous year's JEE papers, advanced paper like 2019. So let us read this first problem and try to solve, and then we'll go one by one. So the first problem says, a free hydrogen atom, after absorbing a photon of wavelength lambda a, this is lambda a, gets excited from the state n is equal to 1 to the state n is equal to 4. Immediately after the electron jumps from n to m state by emitting a photon of wavelength lambda e. So immediately after that, so that means there was a hydrogen atom in the ground state, say n is equal to 1 state, then it gets excited to n is equal to 4th state after absorbing wavelength, a radiation of wavelength lambda a. Thereafter, it gets de-excited to some state n is equal to m. Okay, and during that it is emitting a radiation of wavelength lambda e. Now let the change in momentum of the atom due to the absorption and emission are denoted by delta p a. That means the change in the momentum of the atom due to absorption of wavelength lambda a, and delta p e, that is the change in the momentum, linear momentum, change in the linear momentum after emission of the radiation of wavelength lambda e. If lambda e by lambda a is 1 over 5, which of the following option or option is or options are correct? That means more than one option may be correct. And here H is given as 1 to 4 to or 12,042 electron volt nanometer, and where nanometer is 10 to the power minus 5 meter, and H and C are having conventional, these are conventional Planck constant and speed of light respectively. So you have to see the options. So this is actually a ratio of change in the linear momentum after absorption, delta PA, and delta PE, change in the linear momentum of the atom after emission of the radiation, that is given as half. We have to see whether it is correct or wrong. Then the ratio of the kinetic energy of the electron in the state n is equal to m to the state n is equal to 1 is 1/4. So you have to find out what is the ratio of kinetic energy of the electron in this state. N is equal to m and n is equal to 1 state. Then the emitted photon has wavelength lambda is equal to 418. Whether that is correct, we have to see. And what else? Further, m is equal to 2. You have to find out. That means the state where the hydrogen atom gets de-excited or de-excited to, that is m is equal to 2, that you have to show whether it is correct or wrong. Okay, so let us see what we know. We know E is equal to AC by lambda. Sorry, E is equal to AC by lambda, right? And again, 1 over lambda is R Z square, 1 over N, 1 over N initial square minus 1 over N final square. Okay. I'm sorry, this will be M final square minus initial square. So this is the formula we know for the transition of an electron in the like for hydrogen atom. Okay, suppose there are various energy levels, right? N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4, N is equal to 5, etc. Okay, let us say this is okay. So now the question is, see, the electron was there at the ground state. Okay, electron was there in the ground state, and as soon as it absorbs a photon of wavelength a lambda, it gets excited to n is equal to 4. Okay, so this is there, and immediately after going up to here, it gets de-excited to some level. We don't know what it is, so that is mth level, say. Okay, it gets de-excited to mth level, and that time it emits photon of wavelength lambda. So we can see what we can write is, see, we can actually uh, see, if we just compare these two, this equation and this equation, then we can write uh, 1 over lambda. So E is equal to, we can write E is equal to R H C Z square by lambda E, okay, or lambda A. In general, we can write, this is general formula, and along with that we can write nf square minus 1 over n initial square. Okay, so this is what we can write. So according to the question, see, according to the question, this thing is given already. Okay, we'll go with that. We'll go with that flow. So what we can write, lambda E by lambda A is equal to, what is the ratio? I'm sorry, I think it is lambda A by lambda E. Lambda A by lambda E is given. So lambda A by lambda E is 1 over 5, that is given. Okay, so this side, see, as we had written this E n, suppose some value n, or in general E, let us write E. So we know that it is RCZ square 1 over 1 over n f square minus 1 over n I square. Okay, all right, so this is again AC by lambda. We can just do one thing, we can just take the reciprocal of this, or anyway we are going to take the ratio. So in this case what we can write, we can write 1 over m square. Okay, 1 over m square minus 1 over 4 square. So this is final, this is initial. In case of emission, 1 over lambda means this. Okay, lambda e means on 1 over lambda a here, that means it will be coming here. So this is again 1 over 1 square minus 1 over 1 4 square. So I hope you have understood this, because this is in case of absorption, this is the case for emission. So this is lambda a by lambda e, which is given as 1 over 5. Now it will be easier to do the calculation. Now look, this is 15, 1 over m square, 1 over 16. Okay, so this will be 1 minus 1 over 16 again. So this is 15 by 16 here. Okay, so 15 goes off from both sides. So 1 over 16, 1 over 16. You can just go with 1 over m square is equal to 2 by 16. That means 1 over. So 2 by 16. Oh, what? This is not 15. This is 5. I'm sorry. This is 5. Okay, I think I'll just redo the calculation part. So this is 5 into 1 over m square minus 1 over 16 is equal to 15 by 16. Okay, so this goes as 3. So 3 by 16, and this side 1 over this, and see, it is 3 by 16 plus 1 over 16. This will be 4 over 16, which will give you 1 over 4. So m square is 4, which implies that m is equal to 2. So this was one option. You can see the option D, m is equal to 2, that is correct. That is correct then. Okay. So now if we put the value of m, then finding this lambda e will not be very difficult. So we have got m is equal to 2. So we know this is lambda a by lambda e is 1 over 5. So from here itself directly we can just get this 5 into lambda a. So what is the lambda a? Lambda a, okay, even lambda is also not given. So what we'll do, to find out lambda E, we can directly put in this equation lambda E, 1 over lambda E is equal to R Z square. Z is a new 1, R RCZ square. So RHCZ square, HCZ square will be, okay, this is there. So this is the emission. So emission is happening from, in this way also you can do, emission is happening from 4 to 2. So in that way also you can do. See the, okay, let me find out first what is the energy, change in the energy. Okay, so we'll get, see E4 is minus 13.66 by 4 square, right? So this is one thing. All right, so let us write this 16, and it is going to minus 13.6 by 2 square, this is 4. Okay, so what is the change in the energy? Change in the energy will be, this is initial, this is final energy. Okay, let us take the difference. So minus 13.6 by 4, 16. So you know you will get some value. So this is 4. The minus sign, and this will be a positive sign here. 13.6 by 16. So again we can just do this. So kind of this with the minus, and obviously if we take the modulus of this energy, so this will be 102, excuse me. So this comes as 5.1 by 2. Okay, so minus 5.1 by 2, kind of this. So if you do in this way, or so this is the energy, change in the energy. Now we know AC by lambda. So AC by lambda is the energy. So from here corresponding wavelength we will get delta E. If we just compare this two, then we will get delta E is equal to, sorry, wavelength is equal to AC by delta E. So if we do that, we'll get the wavelength. And so what we have done, delta is equal to AC by lambda E. If we do that, delta E is equal, sorry, E lambda is equal to AC by delta E, change in the energy. So we can see this calculation will give you this nearly equal to 487 nanometer. Okay, and here in the option given, it is given as 418 nanometer, which is not true. This is not true. Now we'll see that kinetic energy, ratio of the kinetic energy. See, the kinetic energy are directly proportional to 1 over n square. Then if we take the ratio of K2 to K1, so n is equal to m, state is n is equal to 2 state, and this is n is equal to 1 state. Now we can take the ratio, so it will be 1 over, so n 2 is 2 and this is 1, so this is 4, so this is also correct. Kinetic energy, ratio of kinetic energy will be 1 over 4, so that is true. Now we have got, okay, so we have got this option all as well. So delta PA and delta PE, change in the linear momentum. Change in the linear momentum ratio is half. So if we know the corresponding, see, absorption takes you through. Okay, so I think changing the momentum can be written as, see, okay, let me go to the next page. So linear momentum, we know kinetic energy is equal to square by 2, okay, 2 square by 2m. Now let us do one thing. Let us take the change in the kinetic energy. So 2p dp by this. So this goes p dp by m. Again, p, we know p square by 2m is equal to kinetic energy. So in terms of kinetic energy, p will be 2 root over 2 mk. Okay. So if we put it here, so it will be root over 2k by m into delta p. So delta p will be root over m by 2k into delta k. Okay, this is change in the linear momentum, I can say. Now we have already found out the uh, kinetic energy. So changing the kinetic energy may be taken in the same proportionality ratio. So K2 by K1, if we take this by this, we'll get in the same proportionality ratio. Okay, so M is anyway same for both. Okay, so this is root over 2k. So this term 2 m by 2 anyway will get cancelled. So it will be, let us take this as constant anyway. So it will be actually k e by ka. Okay, somewhat, okay, with a ratio this, okay, somewhat proportional to this. So this would actually give you ke by, see, we have got the ratio k emission ke by ka. We had got the emission 1 over 4, so 1 over 2. It is 1 over 2, but this part is also there. So this is actually not true. This is proportional, but there is a constant, this delta K, change in the kinetic energy, there will be some value. So this would make this guy not equal to half. Okay. All right. So we'll move on to the next problem. Okay. So this problem, let me just write this problem. So suppose a radon 226 mass number, N88 is the number of proton, nucleus. So radon nucleus undergoes a decay. Okay. Radon nucleus at rest and in ground state undergoes alpha decay to a residual nucleus, that is, so it is radium, this is radon 222, and here it is 86 in excited state. That means this nucleus is in excited, okay, excited state. The kinetic energy of the emitted alpha particle, the kinetic energy of the emitted alpha particle is found to be 4.4 MeV. Then this radon residual nucleus, after that, to have a stable condition or ground state, to come into ground state, this undergoes gamma decay, goes to ground state by gamma decay. Okay, gamma decay. The energy of the emitted photon, the energy of the emitted gamma photon is how much? So this is the question. So what are the parameters given? Parameters given: radium, mass of original atomic mass of radium is given as 226.005 atomic unit. Then atomic mass of radon. Okay, atomic mass of radon also given. How much is that? That is 222 0.000 U. Further, alpha particle has atomic mass 4, and we know 1 U is 931 MeV. Okay, MeV per second, so divided by c square, MeV by c square. C is the speed of light. So these are the points given. So you know here the radium nucleus is undergoing alpha and gamma both the decays. So initially it undergoes alpha decay. Radium goes to radon, and radon is in excited state. So to come to ground state, it undergoes further gamma decay. So you have to find out the value of the energy value of the gamma photon. So here, you know, how do we calculate energy released in any reaction? Excuse me. So we first find out mass defect, right? Mass defect. To find out the energy released in any reaction, we need to find out what is the mass defect. That is delta M, and that is equal to, see, we have atomic mass of this, atomic mass of alpha particle, atomic mass of the residual nucleus. So in generally the mass of the parent, atomic mass of the parent nuclei minus daughter nuclei 22200, these are in atomic unit, minus 4. This is U or AMU, you can write. So this will give you actually 0.005 U. Okay, so this is the mass defect. Then what is the Q value? Q value, or the energy equivalent to this mass defect, that is 931 into this. So if you multiply, what we get? 4.655 mega electron volt, because this is the Q value obtained. Okay, again we know that from the conservation of energy and conservation of momentum, we reach to this equation as well. This is already known to us. So suppose the kinetic energy of alpha particle divided by kinetic energy of the delta nuclei, the ratio of that can be written as mass of the radon to the mass of alpha particle. Okay, so from here actually we will be able to find out mass of kinetic energy of this is radon. Kinetic energy of radon will be found out from here. So m alpha divided by m rn into k alpha, kinetic energy of alpha. This one. So now if we put all the values, these are having values are given. If we put the values, we will get 4 by 222 into 4.4 . So this would actually give you, see, it will again come in MeV, this will give you 0.08 MeV. 0.08 MeV. And see, this is the kinetic energy of the radon. So gamma photon, see the total Q value must have been released this much, right? And alpha particle, sorry, radon has recoil energy of this much. Okay, so what is the energy of gamma photon? Gamma photon is actually released, taking the rest of the energy. So total Q value should be this one, alpha particle and the daughter nuclei radon. So we know the energy of the gamma photon will be equal to this minus 4.44. Okay, so this is alphabetical kinetic energy. This is the kinetic energy of the radon, that means total residual or residual nucleus. And see, defect of this energy will be actually, or excess of this energy will be carried out by the gamma photon, that is. So this is 0.139, sorry, 0.135, that will be 135 kilo volt. This is actually MeV. Okay, so this is the value. We'll go to the next problem. So this problem is also from radioactivity. I'll write in short notation. It was difficult for me to type because there are many mathematical terms which I had to avoid. Okay, so we'll go to the next problem. Problem number 3. So this is also from IIT-JEE Advanced Advanced 2019. In a radioactive sample, I'm just writing, in a radioactive sample, see potassium 1940. This is a radioactive sample, radioactive nuclei that decay into stable calcium 2040 with a decay constant. It has got, for this reaction, it has got a decay constant, say lambda 1, to be 4.5 into 10 to the power minus 10 per year. This is the decay constant for this reaction. Like say potassium, a radioactive nuclide potassium will be decay into calcium, that is stable nucleus, calcium 4020 or 2040. So for this reaction, the decay constant lambda 1 is 4.5 into 10 to the power minus 10 per year, and it can decay into another path also. So what is the path of decay? Another path of decay is given as, see, it goes to stable argon also. Argon, it can go to stable argon also. Argon with decay constant 0.5 into 10 to the power minus 10 per year. Okay, this is another decay constant and another, excuse me. So potassium can decay into two processes. So that is the main point which we have to note here. So there are two pathways for the radioactive nuclei potassium to decay into. One is that it can go directly to stable calcium with decay constant lambda 1, which is given here, and another path is that it decays into argon with decay constant lambda 2 is equal to 0.5 in 10 to the power minus 10 per year. Okay, now given that in this sample, I'll write now, it is given that in this sample, means this radioactive sample potassium along with the other product, in this sample all the stable calcium 2040 and argon 1840 nuclei are produced by the potassium 4019 only. That means just by decay process from this nucleus in two pathways. So that means, you know, like there is a sample where both three elements will be there, and all the elements, stable elements of calcium and argon are actually produced by this potassium alone. Okay, so that is what is said here. Now the question is, in time t into 10 to the power 9 years, if the ratio of sum of stable Ca and argon. Okay, so this is 2040. Similarly, this is 1840. Nuclei to the radioactive residual, that means residual radioactive okay, 19 nuclei is 99. Then the T is equal to how much time? You have to find out what is the time. Here it is given that ln 10 is equal to 2.303. This is given. So I hope you guys have understood this question. I'll just simply repeat the last part what I have written. So these are two pathways for calcium to decay into two stable product, calcium and argon. And in the sample it is said that the sum of in the sample the whole calcium nuclei and all the argon nuclei are just produced by calcium. Now after these many years, if the sum of the if the ratio of the sum of this nuclei and this stable nuclei to the radioactive potassium nuclei is 99, then what is T? Okay, we'll solve this problem. So we have seen potassium goes to calcium. Okay, it goes to argon, and this is lambda 1, this is lambda 2. We know that. So what is the total lambda decay? Because we see in the same time frame, okay, there is actually equal probability of getting decayed into both. So I can just take lambda 1 plus lambda 2. This is the total decay constant of the radioactive nuclei. And now we'll see how it is. So lambda 1 was 4.5 into 10 to the power minus 10 per year. Okay, and this is 0.5 into 10 to the power minus 10 per year. So this can be written as 50 into 10 to the power minus 10 per year. Okay, so we get this part. I'll erase then. So sum of the decay constants are, so sum of the decay constant is 5 into 10 to the power minus 5, sorry, minus 10 per year. Okay, now we know the general formula. After some time t, how many nuclei, radioactive nuclei, these will be remaining in the sample? That is the initial number into lambda t e to the power minus lambda t, right? So in the problem, you know what is given? N minus n0 by, sorry, in the given problem, what is given, you know, in the given problem. So if we just see in time t into 10 to the power 10, 99% of k gets decayed. Okay, decayed. So the undecayed will be how much? So undecayed part of the sample is equal to N is equal to N0 minus 99 by 100 into N0. That means it is N0 by 100. So this is given as, okay, this is given. Now what we need to do is, see, N by N0 from this particular equation, N by N0 is how much? Okay, so this is undecayed. So this undecay, this N is actually undecayed part, right? So N0 by 100 we can write here, and here it is N0, this is by lambda T. See, this N0 will cancel each other, so we will get e to the power minus lambda T is equal to 1 over 100, so lambda T is equal to 100. Okay, so e to the power lambda T is equal to 100, right? If we take ln, so we'll get lambda T ln 100. ln 100 can be written how much? 2 ln 10. 2 ln 10. Okay, 2 ln 10 can be written, and T will be 2 ln 10 divided by lambda. And see, in the question it was given ln 10 is equal to 2 point, so 2 into 2.303 divided by lambda. Total lambda is 5 into 10 to the power minus 10 per year. Okay, so this will be 2.303 into 10 to the power 10 divided by 5. Okay, so if you do the calculation, how much you get? Let us just do this. So 606.4 point this. Okay, and we have to, so we just take here 46.06 into 10 to the power 9 divided by 5. So this, it is 945, 1 here it is 0, so 9.2, so around 9.2 into 10 to the power 9 years. This is the time. Okay, okay, so there were options given. I think I have skipped this options, or I have forgotten. No, you have to find out the time t. What is the value of t? So total time is, so t into 10 to the power 9 it was given, right? So t into 10 to the power 9, so this t will be just this value. Okay, so total time is 9 into 10 to the power 9 years. Already 10 to the power 9 years was given, so you need to find out what is the value of t. So this is t into 10 to the power 9 years was given, so we need to find out what is t. T is 9.2 then. So t is equal to 9.2 years. Okay, with this we'll stop it here for today. We'll take up more questions from remaining papers, JEE advanced papers, in the next classes. So thank you for your patience. Bye for today.